Okay, so hey guys, today we're talking with Robert as he studies for, his data science interviews. We're going to start off with linear regression. He had some math questions for me, so hopefully I'll be able to answer them. And yeah, let's just jump right into it. Yeah, so go ahead, Robert. What's going on?
Okay, so a lot of this is going to piggyback off of the linear regression video that you put together and the notebook that went along with that. But I just want to
Sweet.
kind of clarify a lot of the math that was going on behind the scenes there. So we start off with our linear regression equation here. So exactly the same that you had in your notebook. And then they go on to the matrix form of, I need to write this in my own book here, the matrix form of y equals 1 x.
So just a pop quiz, why is there a column of ones in the X matrix?
That is the coefficients for our intercept or beta 0 term.
That's
Because
right. So we had a column of ones for the
yeah,
intercept. Yeah.
yeah, because our x terms do not have beta 0. They start at beta 1.
Right, and then you can see in the n cross p plus 1 in the middle of the slide that p plus 1 instead of p is because we have an intercept. So there's p features and then one intercept.
Yes.
And p plus 1 total features.
Yeah. Wonderful.
All right, just an easy one to get our confidence up.
Yeah. No, we've been working together for a while. You have taught me well. Okay. I'm just copying a little bit of like matrix stuff here, just because actually no, let's comes up the next slide, right? Okay, so here we go now. Right. So here's our whole kind of matrix algebra behind it all, right?
Yeah, so just to summarize, this is actually linear regression, basically the initial setup. Again, we have an extra column of ones because of the intercept. It's kind of written out a bit more like verbose than usual because you might be used to the equation y equals x times beta plus epsilon, but they're writing out the y, x, beta, and epsilon as vectors and matrices. Well, everything's a vector besides the x, which is a matrix.
Yeah. No, it's very verbose. But this is what I wanted to do with you is kind of go through because we're really close, like with working with you and going through your notebooks and the videos. Like at first I was very not confident about all the math stuff, but you've been really, really helpful with everything. I'm just finishing writing this down, and I got the epsilon 1s, epsilon 2s, the n. Okay, great. And then this is what we got into. So this was an interesting question that this was an interesting thing that they brought up in their class and in their material, just saying like, I don't think this was worded properly, which is what I wanted to talk to you about. But the model is said to be a linear model. What is the linear relationship in? The model is linear in x. The model is linear in the coefficients beta. Now, what was explained to me is that this is actually still a linear equation, a linear model, even though it's cubed, because
yeah, we can talk about that, but that's more.
Yeah.
Let's. So, what did you have questions on this one first?
No, really.
So equation 4 is all good for you.
Yeah. Equation 4 is all fine for me, because basically we take the dot products, right? Like when you do the matrix multiplication. We take like this row, I guess it's going to be this one times that one times this one.
Yeah, I mean, if you're comfortable with dot products, and if you want to understand this, you should be comfortable with dot products. Basically, you'll take the dot product of the, like say the first row being left to right, so horizontal. So the row would start with 1 and end with x1 comma p.
Yeah.
And you would dot product that with beta. So the beta would be the column. And so, yeah, it would be x, the first row of x, dot product beta, and then plus epsilon 1. That would be like your first coordinate.
Yeah. And so just to make sure that I do know what dot product is, we're going to take 1 times beta naught plus x1 1 times beta 1 plus x1 2 times beta 2, blah, 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 all the way down, correct?
That is correct, yeah.
Yeah, and then we'll get like a single integer sum because we're adding everything up together.
Yeah, well, you said integer sum. It could actually just be, a real number. But yeah, exactly. A
Yes, yeah,
scalar
yeah,
sum.
yeah. But we just get one thing. I still have trouble with like the matrices, like we just get one thing, right? I
Right,
guess
dot product, the output of dot product would be a single scalar,
yeah,
not a
it's always
single
a
real
scalar.
number.
Yeah, we did it with the PCA. I think it came up there as well.
Yeah.
Because again, this would be now following the matrix multiplication rules, this would be an n by p matrix here.
Ooh, okay, so x is n by p plus 1. And then the other one is p plus 1 by 1, beta, right?
Yeah.
So
So we're
then the
gonna get
product will
a
be n by
p.
1,
So be a n by 1 will be our final matrix.
just like the epsilon vector.
Yeah. Yeah. Aha. Yes. Yes.
Oh, yeah.
Yes.
Else we
Yeah.
have issues because we're adding things that don't have the same dimension.
And they're just doing p here, right? Like they're, because I mean, like you said, p plus 1, but they're just
Well,
doing.
there's really like a 0th column because they're all ones. So
Yeah.
really there's p plus
Yeah.
1 different.
Yeah. Yeah.
And you can see it in beta, actually. They have beta 0.
Yeah, and they had p plus 1 here. And this is the stuff that I wanted to kind of like go into nuances because there are typos and things like that where it's just like, hey, let's really kind of
So
drill
far, I
down.
didn't see a typo, but maybe one
Yeah.
exists.
Well, no, here they did p plus 1, but here
Right,
they just do the ones and as 0 and then just p, right? It's not like it's p plus 1. For
well, no, there's p plus 1 columns, even though the indexing starts as 0, which is fine.
Yeah. Oh, okay. Gotcha.
So if you start at 0, you'll have one more than the final index.
Yeah. Cool. Yeah. So they were saying that an equation is linear if it can be broken down into this type of composition. So this equation works, whereas like y equals cosine beta x would not work.
Right. So this y equals 1 plus 3x cubed. So what you would do if you went back, well, you would create a matrix, kind of like the one in, exactly like that one.
Yeah.
Would be all ones in the first column, and then the second column would be kind of just like x1 1 cubed.
Yeah.
Times 3 actually, because it was 1 plus 3x cubed.
Yeah.
So you can actually create, you can actually model like cubic relations by just cubing the features. Like, each column can be cubed.
Yeah. Yeah.
So you can think of that as linear, and 1 is the intercept, and then it's linear and x cubed actually. It's a little weird to think about because a cubic equation is not linear very much.
Yeah. I know a lot of people kind of turn their heads at that one, so it's kind of a kind of thing of contention.
And then cosine, pretty much you shouldn't think of it as linear. I mean, it actually is linear and like infinitely many variables, but no one's gonna want you to do that one.
Yeah.
You can do the Euler expansion, but let's not worry about that. Yeah. So, but that's a good example. Cosine you wouldn't really think of as a linear function.
Yeah. Okay, great. So now we have this down. It's like, okay, how do we find the coefficients? And we went over these equations. I mean, we went over the least squares estimator ourselves the other day, right? Where we kind of did that. And we said that this kind of becomes the dot product, right? Because we want to minimize our loss function.
Yeah, okay, let's go over this one.
Yeah.
Right, so the first displayed equation is literally just the mean squared error.
Yeah.
So that actually have nothing to do with linear regression. I mean, it has something to do with it, but it's more general. Like you can use the mean squared error in a neural network or in other machine learning algorithms.
Yeah.
And then in the second displayed equation, that is actually used in linear regression because it's saying that your y hat or yi hat is actually going to be the dot product of your, feature vector xi with
times
beta.
betas.
Yeah. So that's actually how linear regression is set up, is that you're trying to predict something using a dot product.
Yeah. And when we do linear regression, we don't actually use gradient descent. We take advantage of the dot product right here, right? That this betas are going to equal the transpose of x times x inverted times the transpose of x times y.
Right, yeah, you can just call that the least squares solution.
Yeah.
Equation
Okay.
6. Yeah, don't worry about, I don't eat, well, okay. I guess by now
No,
I
no,
remember
no.
the formula, but I wouldn't demand myself to remember it. I just happen to know it. But
Okay. I would
yeah,
like to demand myself to know this because again, it came up in a couple questions we did in the How to Ace the Data Science interview book. I
I
guess
mean, I
free.
can show you how I remember it, but
Yeah.
uh,
No, it's not that bad. It's just x to the -1 xty.
yeah,
I
but
mean,
it's
if I could,
actually, it's a lot simpler
yeah. I mean, if
because
I
you're
could
trying to
remember.
solve
Sorry.
x beta equals y.
Yeah.
And then it turns out for least squares, you multiply both sides by x transpose.
Oh, okay.
It's a little weird. And
Yeah.
then that's how you solve. Because, yeah, I mean, okay, so first of all, that's the least squares solution, beta. It's okay, yeah, you said it's given by a dot product. It's actually given by, I guess it's technically like a matrix multiplication. Like x transpose x is actually going to be like p plus 1 by p plus 1.
Yeah. How did we write it last time? I'm gonna go back to our notes here. I think we did it. Yeah. We said that the sum of the squares equals the dot product, which is just the transpose of a matrix times itself.
Sorry, say that again?
We said that the sum of the squares, I think in our last lesson, is like the dot product of a matrix, which is just like
Oh, okay, that's something different. So equation 5, you can actually write that as a dot product of, uh,
this one. Yeah,
yeah.
equation 5. Yeah, that's what we did. We wrote it as a dot product.
Yeah, so it's y minus x times beta.
Yeah, okay, yeah. So this is the dot product here. This x times beta.
Well, that is a dot product x, but you can actually, yeah, so it's a little funky. Let me see. Uh, maybe I can share my screen for a sec to
Yeah,
kind of
yeah,
explain what
yeah,
I'm
yeah,
talking about.
yeah. Let's do
Uh,
that. Yeah, no, these are the things I wanted to get into the nitty gritty about and really kind of clarify.
yeah.
Because
Uh,
again, I was just like, well, they're not so they don't actually use gradient descent in linear regression because I guess this is computationally more viable to just do the least squares solution.
so you're saying gradient descent? Well, I wouldn't say that it's, no, I wouldn't say that at all.
Okay,
I
but
mean, you
we
have
don't
to,
actually use gradient descent in practice for linear regression because what I've seen, it seems like they always talk about this is the solution, this is how it's solved,
a bit weird that
or
they do that, yeah.
huh?
It's a bit weird they do that. I would use
But it,
gradient descent probably, even though I know the solution, unless I had a pretty small, a pretty small
so
matrix.
why do they keep on bringing up the least squared solutions then? Is it just because it's nice theoretically and it happens to match with the maximum probability likelihood as well? Like,
I guess it's because you can actually, I mean, you can find the exact solution, which is nice, as opposed
yeah,
to gradient descent, which you only get like, pretty, very, very close, like close enough that you know,
okay, yeah. Oh
wouldn't
yeah,
really make
again,
it.
yeah. Because if you have like a 2 billion entry matrix to take the transpose and inverse and stuff like that, that's going to be pretty computationally expensive compared to gradient descent in that case.
Right.
Yeah.
All right, cool. So let's load up this guy.
Yeah.
So let's import NumPy. Let's just do it in Python so we get practice with Python while we're doing it.
Okay.
I'll also explain what's going on. Uh, yeah, don't make fun of me too much for having a global install of Python. All right. So the equation was, let's make up some numbers here. So I don't think why should look like this one. So let's see. We had should we do this here? Maybe it doesn't matter that much. Just like this. And do x at beta. There we go. Okay, so x is like the x from your notes, beta is like your beta, and y is like this. It doesn't matter what the actual numbers are, but just so we have something to plug in.
Yeah.
So the equation 5, right, from earlier was like actually just np.sum of, it was actually this, yeah, exactly. Does this look familiar? Actually, let's even write it in 2 steps so it makes complete sense. So let's write this as y hat and y
Yeah.
minus y hat.
Yeah.
Right?
Yeah. No, that makes sense.
So right, this is except for I did a mistake. This should be like the squares, right?
Yeah.
Y hat, this is from linear regression, right? We just do matrix multiply x with beta.
Yeah.
And then to compute the residuals, we compute the sum of the squares of the differences of the. So this is like this is the residual y minus y hat.
Yeah.
As it's a vector, we square the entire vector, and then we take a sum. Right. So what we were saying is that you can actually write this. This guy here is actually just the same thing. This was what was in the notes. This was equation 5, at least part of it. Actually, the whole thing. What we had said last time is you can actually write this as a dot product. Sometimes people do, and it might be a little confusing. So it's actually just the dot product of y minus y hat with itself.
Because it's squared because of the squared fellow.
Right, the
Yeah.
squared and the
Yeah.
definition of
Yeah. I
dot
remember.
product.
Yeah. And then. Yeah.
It's not exactly working. Maybe I have to do transpose or something. I don't know exactly here. There we go. Then it works.
Yeah.
Yeah, so it's the dot product, not of the vector with itself, but the transpose of the vector with itself.
Yes.
So this was something you had brought up, and you said it was confusing, and it was in some textbook, basically written like this, and you're like, "What the heck is this?"
Yeah.
But then we had worked out that it's actually just a fancy way to write. So basically, anytime you have like in linear algebra, a lot of times you can write things very concisely, which can be confusing or like very helpful depending on the situation. As you get more experience, this is kind of useful to write it this concisely. However,
Yeah.
when you're first
Let me
getting used
actually
to
write
it,
that down.
right?
So it's y minus. Hold on. Let me do this. So we get y minus y hat
Yep, the residual.
squared. No, I'm just starting. No, I'm starting this squared, and this equals y minus y hat times y minus y hat, and we know that we can solve this by just taking the dot product.
It turns out that the sum of the squares of a vector is the same thing as the dot product of the vector with itself.
Yes.
That's actually the
Yeah.
fact that we're using.
Yeah. That was the formula. Yeah. Okay. Yeah. So the sum
Let's
of
actually see it. I'll do it while you're kind of working.
Yeah. Sum of squares of sum of squares is equal to the dot product.
The vector, well, I guess the transpose of the vector with itself.
Yeah, is to the transpose of vector with. So is that where they get the beta transpose inverse fellow from for the least squares solution?
No, that's something different.
It's something. Okay, yeah. So no, it was that transpose that kind of like is what made me think that that's where it was coming from.
Yeah, I'll explain that one
I see.
after.
Yeah,
Yeah.
yeah,
So this is kind of the thing that the math fact that's going on behind the scenes is that the sum of the squares is the same as the dot product of the transpose with itself.
yeah. And because we're doing the transpose of the matrix with itself, we're always going to get a scalar, correct? Is that
Yep.
like I imagine, huh?
Yeah.
Yeah, yeah.
And we
Now is
had
that
talked
because
about what happens if you like if you see my screen, if you accidentally put the transpose on the second guy,
yeah, it doesn't.
you'll get a 3 by 3 matrix. Well, yeah, you should get a 3 by 3 matrix. I think it's just because
Yeah,
um is the way NumPy is working.
yeah.
If I had done it properly, it should be this one. NumPy was too smart, actually. It knows,
Yeah.
but
But
if I force it to do it the way I wanted it to do it, then it gives a 3 by 3.
yeah, but I mean, if we had a 3 by 3 matrix times the transpose of itself, we would get a 3 by 3 matrix, not a scalar, correct?
Correct. Yeah, we want it. Yeah, exactly.
So how does that fit into?
I'm just saying this is a common mistake. Don't do this.
Okay, yeah,
Yeah.
yeah. Oh yeah, no, I'm saying that that solution comes from something totally different. Okay, cool. No, that all.
Now for
Yeah,
least squares, I can explain a little bit. So let me uh
yeah, yeah. No, no, do
do
your
that
thing.
one. So I can write this pretty quick, I think. Yeah, so this is the formula for least like the starting situation for least squares.
Yeah,
That was the verbose thing they wrote.
yeah,
So actually what we're trying to do is if you think of epsilon as pretty much close to 0,
yeah,
we're actually trying to solve y equals x beta. This is the equation we would like to solve,
yeah,
right? So what you might think, what you would think to try, or what I would first try, is just to do x inverse y. This isn't right, but I want to at least show it.
hmm
Like why? And I guess this is a good question. Why can't we just do this?
yeah.
That's a question for you.
Well, because these are matrices, not algebra. You
Well,
just
no,
can't.
we can invert a matrix sometimes, right?
Yeah,
So why can't we?
sometimes you can invert a matrix.
Yeah. Why can't we in this situation?
Um, dimensionality would be something that would come up on my mind. You need to ensure
Yeah.
that the values are the same with the betas.
So actually,
And when
x
you
is
take the inverse, you actually can't do that.
yeah. One reason why we can't take the inverse is that for a matrix to be invertible, so that you can take an inverse, it has to be square.
Yeah.
But your data matrix typically is very much not square.
hmm
Typically, you have a lot of data points and a few features.
Yeah.
So this doesn't make sense because you're trying to invert a matrix that's not square.
Yeah.
So the way that math people
Oh, so you take the transpose, multiply it by itself to get a square matrix.
exactly. So
Then you
yeah.
then you can invert it.
So it turns out the trick that actually works, surprisingly almost, is that you can just multiply both sides by. This is wrong, so let's get rid of that one. We start with this one, y equals x beta, and we just
Yeah.
multiply both sides on the left by x transpose. And then it turns out that this x transpose x is square.
Hold on. Yeah,
Yeah.
x transpose times x times beta. Yeah, yeah. And then it turns out that what squared?
This x transpose x, the thing that's multiplied by the beta is actually
Yeah.
a square matrix.
Yes, that is a square matrix. Yeah.
So we can at least we can hope to invert it and apply the formula that was on your slides.
Oh, I see. So, ah, I see where that equation comes from now. Okay, cool. Yeah. No, that makes sense. It was just written a bit differently. Yeah. No. Now I see where that -1
Yeah, exactly. So then
exponent comes from. Yeah.
to finish it out,
Yeah. That no, this is exactly what I wanted to do with this lesson, man. Was to fill this stuff in. Yeah.
is we invert x transpose x. I usually like to keep things like on the top equation with and then I just say solve for beta, but a lot of people do like to actually show the inversion.
Oh yeah. No, 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 that's fine, man. No, 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 that works. That works. Yeah. Okay. No, this is all okay, great. Let me kind of go back and share my screen then, I guess. It's kind of
Go for it.
yeah. No, but that really helps. Like again, like knowing where some assumptions end and others begin is really kind of like this kind of data science. You're kind of like a jag, like we're going to take some linear algebra here, but we're going to use some other stuff here, and like so now I'm understanding all this, right? So here we're trying to minimize the residuals, right? And we got there
Minimize
because
the sum of the squares of the residuals. Yep.
yeah, here because that gives us our betas, right?
Hmm.
Because that's kind of what's going on. And this comes from the least squared solution. This is from our like error function, I guess. Um, but then we get to the same thing using the maximum likelihood estimator. We don't have to go that heavy into it. What's this fellow mean again? This guy?
That big pi, it's capital
Yeah,
pi in Greek. It means product.
product. Yeah.
So like sigma means sum.
So we multiply all these guys together.
You don't see it very often because it's actually not that often in practice. You're multiplying a bunch of things together.
Yeah, I know.
But here it makes sense because these things are probabilities, and then
Yes.
the product of well, if you basically it comes down to the fact that for independent events, the product of the probabilities represents like the joint probability.
Yeah. Yeah.
So that's why we see a product here.
Yeah. And this has like three assumptions of the linear regression model all in one. I've come to learn. And basically I understand what's going on here, that they want to take the derivative, right?
It's pretty complicated what's going on. A lot of math.
It's not that bad, like here, so it's like, they're taking the log.
Well, you first have to convince yourself that MLE is a good thing to look at. Then there's this log trick
Yeah.
to
Oh,
turn the product into a sum.
I'm just convinced that whatever they show me is what, they figured it out. I'm just here to be a parrot.
So, anyways,
like,
you probably don't need to know this derivation, but I guess what's useful to know is that
we're trying to minimize, we like is we get back to the same place. Like we're trying to minimize this, because minimizing this maximizes our log likelihood, right? Like we get back to this trying to minimize this yi xi beta, right?
yeah, they're showing another way to think instead of thinking of it as because it kind of seems a little bit arbitrary to like why should I minimize the sum of the squares of the residuals?
Mm-hmm.
Why not the sum of the absolute values of the residuals? Or I don't
Yeah,
know.
yeah. Well, I mean, they do that, right? Like that's the mean absolute error.
Right. Or maybe even something else. So why
The percentage. What's the other one? The MAPE, right? Mean absolute
maximum
percentage error.
priori? I don't know.
Yeah.
Yeah. So yeah, I mean, they're kind of trying to justify a little bit like, uh, why are we doing the mean squared error?
Mm-hmm.
And actually, the mean squared error is the only one that you should do if your assumptions are true, and that the errors are assumed to be normally distributed.
Yes.
And they're actually explaining here, and all this math actually eventually shows that if you do assume those epsilon i's, if you remember from the
Yeah.
equation.
No, that's what I was saying. Like this only works if this is here, right? If epsilon is assumed to be normal with a mean of 0 and a standard deviation of 1.
Of sigma, it doesn't matter. It
Sorry,
doesn't have to be a one.
sorry, sigma. Yeah.
It just has to be constant over different epsilons.
Yes. Yeah.
But
And that's where like the homostaticity assumption comes from. That's where your normal distribution of your residuals comes from, right? That's where your normal distributions of y come from. All kind of comes from
yep.
from this kind of stipulation there.
Yes, exactly. And then just from this, stipulation, as you say, you can actually derive that you should look at the mean squared error.
Yeah.
So
Because here,
it's
like
really
we want to
saying something.
maximize this, but because all this is to the negative exponent, right? It was
We want to
this,
maximize. Do you know why that's the formula, or where's that coming from?
yeah, I do know why. We went through it in like the pre-videos. This is the probability that you're gonna find something on a Gaussian
Exactly.
distribution. Yeah.
If you like Googled, you don't have to, but if you Googled like normal distribution and looked at the wiki, this formula would pop up pretty quickly.
Yeah, yeah. You know what? It came up with the white paper I'm doing for my boss right now for the quant research, because we have to calculate the probability of some normal distribution given some y values. We got to
Yeah,
here.
normal come up pretty
Yeah,
much
fucking ugly.
anywhere in applied math.
ugly equation to work with. You have to find the derivative of it, which nobody knows, by the way. You have to use Mathematica, and
What? No, the derivative is fine, and you can compute the derivative.
Yeah, or sorry, the integral. No, we
The
want to find
the integral might be a bit trickier.
Yeah, no. The integral is like a defined function on Mathematica. It's only, I think it only works from negative
ERF
to
or
positive
something.
two. Yeah, it is. It is the ERF. Yeah.
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 That's fine. We don't have to.
yeah,
We don't have to integrate these things.
Yeah. No, but yeah. So it kind of gets us back to the same place, right?
Yeah, which is nice.
Yeah. So what are the main ideas behind least squares solution and maximum likelihood? It's that we need to minimize the residuals, right? That's what we're looking to do.
Well, minimize the sum of the square of the risuals.
Yeah,
minimizing the residuals doesn't make sense by itself.
Yeah, sorry, minimizing the sum of the squares of the residuals. Why do they provide the same estimator? I think because they follow the same assumptions, right?
Well, they follow. Why do they happen to provide the same estimator? It's because of all the math that they just showed you.
Yeah.
They showed that maximizing those product of probabilities is actually the same as minimizing the sum of the squares, which is not obvious.
Yeah, okay, great answer. Yeah, that maximizing the probabilities is the same as minimizing the residuals, which is what's done in the least square solution.
Exactly, which is,
yeah,
pretty maybe surprising if you haven't seen it.
Yeah, no, it is. So now they go into all this inference stuff, which I don't think I need to know. Like, this is getting into like t values and z statistics, and
I had the YouTube video on it with the p values. So
yeah, I thought you would, because here's where the p values and the confidence intervals come in.
Because while you might not need to know it, I probably am expected to know it. So I had to look at it at some point.
Why would you be expected and not me?
Well, I'm supposed to, have the PhD in math, so I should know.
Oh, okay.
Pretty much any math that's, going on with like linear regression, like the.
So should I know this then, or
no? What I'm saying is I should be expected to know it because I'm supposed to be an expert or something at math, so I should be able to figure it out.
Yeah.
But if you're just like trying to get your first job in data science, I wouldn't worry about it too much.
Okay. Yeah,
I mean, it is nice to know. If you're comfortable with statistics, I would recommend to have a look. But
yeah, I mean, I think for now, like I just want to get the broad strokes down, which is what I
think
wanted
that's
to get
fair.
from.
I agree with
Yeah,
that.
like from this time with you, and then we can always circle back in a little bit if I'm still looking for that main job, and I need to get there with that.
I'd say let's call this video here. So I'm going to end this video.
Yeah. Good call.
And then